All right, so I'm going to pick up where we left off last time. We are talking about, simple circuits with resistors and how to apply Ohm's laws and Kirchhoff's rules to them. So we have this situation where we have, and what I want to do today is just try to get to the point where we can simplify fairly complicated circuits. Excuse me, I'm just trying to get my controls under control here. Okay, where we can simplify fairly complicated circuits. So the first thing that I want to do is take a look at this, a circuit that we've looked at a couple of times over a couple of lectures, where we have two resistors hooked up head to tail like this, with a potential difference across this group of resistors. So we have some battery that's providing a potential difference. A current is flowing from that battery through resistor 1 and through resistor 2. We know from Kirchhoff's junction rule that the current that's flowing through R1 and R2 is exactly the same. It can't escape anywhere from the circuit. We have no splitting, we have no junctions. We have a simple junction in the sense that we go into a resistor and we come back out of a resistor. But nothing changes in that kind of a situation. So the current going in is the current going out, and the current going into R2 is the current going out of R2. And in the end, we have the same current all the way around the circuit. This kind of situation where the current is the same through these two resistors is called a two resistors in series. One thing that I have to be careful about warning you is, even though the current is the same between these, the voltage across them is not necessarily the same. So if we had a 10 volt battery across this, I know that there will be 10 volts from this point to this point, but I do not know that there's, I definitely do not know that there's 10 volts across R1 and there's 10 volts across R2. It's just that there's 10 volts total across the combination of these two. Okay, so keep that in the back of your mind. With series resistors, the current is the same through them, but the potential across them could be different. Getting back to the task at hand, if I want to analyze this circuit, I can make a simpler circuit, an equivalent circuit, by creating a combination of these two resistors, R1 and R2. I'm going to call it R total. I haven't done anything to the battery. I haven't done anything to the current that's being drawn from this battery. I've just simplified this two resistors here as a single resistor called R total. And I'm going to skip the derivation here. If you want to see the derivation, it's really kind of simple. It's kind of straightforward, but I don't know that it brings much to the conversation. You can look in your text. It just takes a half a page. The total resistance equivalent of this combination is just the algebraic sum, R1 plus R2. So if I want to simplify this circuit, I can say, hey, I have these two resistors. Well, this circuit here, as long as I say that this R total is R1 plus R2, is going to behave exactly the same as the first circuit, and it's a lot easier to analyze. So, and I should be careful. There's nothing special about two resistors. I could do this for 3 resistors, R1, R2, R3. I could do this for 10 resistors, all of them head to tail with the same current flowing through each of them. If they're all in series, then I have this kind of simple algebraic sum. I just add them up, right? So this is my definition of resistors in series. When the current is the same through all the resistors and they're hooked up head to tail like this, then your resistors are in series, and the equivalent resistance is going to be given by just the algebraic sum of each of your individual resistors. To allow for the fact that I could have 5, 10 million resistors in series, that's what this, you can almost not see it in my notes here, but this dot, 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 this could go on for as many resistors as you want to apply this formula to, okay? So that's our first case of trying to simplify a complicated circuit if I have a different complicated circuit here, notice this looks kind of like, oh, I threw a bunch of resistors into a circuit. It's kind of like what I did before. But if you look closely, this is much different. The potential across these three resistors, R1, R2, and R3, here, they're all connected by the same wire. And remember, one or two lectures ago when I introduced these circuit diagrams, I specified that we're supposed to believe that there's no voltage drop, there's no resistance of these wires. They're perfect wires, and all the resistance is contained in these, jaggedy symbols, the resistance symbols. So the potential across all three of these is the same. It's whatever delivered by the high side of this battery. And down here, the potential is all the same. It's whatever delivered by the low side of this battery. So all three of these have the same potential difference across them, which is different than the situation with the series resistors. And the other thing that I can notice here is that I have this circuit here. I'm going to try to replace this with an equivalent simple circuit. The current that is coming out of this battery, right, flows along here. It splits between here, between here, between here, depending on that resistance. If you think of this as the flow of water, and resistance being how wide or how thin the pipe is that the water's flowing through, the current through each of these is going to depend on the numerical value of that resistance. In short, the current through each of these resistors is not necessarily the same, unless they have the same exact resistance. But in general, they're not going to have the same resistance. So you're going to have a different flow of current through this, a different flow of current through this, and a different flow of current through this. All I can say right now is from Mr. Kirchhoff's junction rule, is that whatever current came out of this battery splits between the three of these, and the current through this one plus the current through this one plus the current through this one is equal to the current that's coming off the battery. Okay, so this is the definition of resistors in parallel, and we get a slightly more complicated situation where if I want to find the equivalent simpler circuit to replace this rat's nest of three resistors, what I'm going to do is add the resistance in reciprocal. So instead of just adding them algebraically as the sum, I'm going to first take the inverse of each of those resistances, 1 over R1 plus 1 over R2 plus 1 over R3. And I stopped in my picture with 3 resistors, but there could be 4, there could be 5, there could be 10 million in this configuration. So that's the signified by the ... that this could go on forever. And this gives you the reciprocal of the total equivalent resistor. This looks a little bit weird in its abstract form. I'll show a numerical example in a moment, which I hope just kind of blows away any hesitation that you might have. So one thing that I should be careful about, I think your book calls this the equivalent resistance when we're replacing these, individual resistors with something, a simpler resistor that behaves exactly the same way. The book calls it, I'm pretty sure, the equivalent resistance. Sometimes I call it the total resistance because it's kind of, I'm combining them together. I hope I don't confuse you with that, but they mean the same thing. I'm meaning the same thing, that this total resistance or the equivalent resistance, please, in your head, just translate that to mean the same thing. Okay, so let's take a look at some examples. So, again, in your participant window, there's a way of saying go slower, and reacting. You can use the chat, you can use the audio. Feel free to interrupt me as you go. That go slower, it might feel a little bit weird to, it sounds like a command. So if you want, just in your head, you can imagine that says, please go slower, and I will absolutely go slower if you punch on that. So here's our circuit. We have a 3 resistors in series. The current flowing through them is being drawn off this 12-volt battery. It flows through the first resistor, flows through the second resistor, flows through the third resistor, and then returns back here. They're in series because the current's the same all through all 3 of them. The question that I'm asking is, I give you the 3 resistances, and I give you the voltage of the battery. what's the current that's being pulled off this battery? I want to know, am I going to just drain my battery in 10 seconds, or is this going to run for a while? And in order to do that, I need to know what is the current that I'm pulling. So you can imagine this is like 3 light bulbs that I'm trying to power with this 12-volt battery. So what do I do? First things first, this is the question that I'm trying to answer. What is I? What is I? What is the current that's being drawn from this battery? So the first thing I do is I take these 3 resistors. They're in series because they have the same current flowing through them, and I just algebraically sum them up, 15 plus 30 plus 23, and I get 68 ohms. Okay, so that's the first part of my problem, is finding the equivalent circuit. I've got that. The equivalent circuit is now this. The voltage being applied from the battery is 12 volts. That doesn't change. The current being pulled from that battery is still the same. It's still the number that we're trying to find. But now we have this simpler circuit, which I can analyze because, hey, I know Mr. Ohm. Mr. Ohm told me how to do this. He just says, use my law, which is I called Ohm's law. And here it is right here. I equals the potential difference divided by R. I know what the potential difference is. It is 12 volts. I know what the resistance is. It's 68 ohms. So now it just comes down to this calculator exercise. 12 volts divided by 68 ohms is 0.18. And there's 2 ways that I could figure out the units. One is I could memorize that a volt divided by an ohm is an amp. Or I can just remember that if I do start with SI units, I'm going to end with SI units, and the SI unit of current is amps. I started with volts, which is the SI unit of potential difference, and I started with ohms, which is the SI unit of resistance, so I get amps in the end. Okay, so that's how we solve this kind of slightly more complicated circuit. I have 3 resistors in series. I want to know what is the current first, get the equivalent resistance, and then just apply Ohm's law to figure out what's going on here. Okay, so in the end we get 0.18 amps. You might also see this sometimes as 180 milliamps because 10 to the minus 3 is a milli. Try not to get confused by these SI prefixes that are often used. Okay, so if there's no questions on that, I'm going to move on to our next numerical example, and that is, hey, I have 3 resistors again. Nothing special about the number 3, but it kind of is more complicated than the least non-trivial example of just 2 resistors. But I could apply this logic to any number of resistors in this situation. So what I'm going to do first is, hey, I look at this circuit. I have 10 volts provided by the battery. That 10 volts is being applied along these perfect conductors to every point here, and this side of the battery is being applied along this perfect conductor to every point here. So I have 10 volts across this guy, I have 10 volts across this guy, I have 10 volts across this guy. And the thing that I mentioned before is we have a current that's being pulled by this circuit from the battery. It's coming out here. But then we have a junction here, we have a junction here, and then we have a passage through this right here. So we have 2 junctions. That current that's being pulled off the battery is going to be shared between this, this, and this. So I don't know what the current through each of these resistors are. I know that the potential difference across each of them is all 10 volts, but I don't know that the current is going to be equal. I actually know that they're going to be different. Because if you think about this with the analogy that we used last time, this is kind of like the flow of water. And our current is a fluid that's flowing from a high level to a low level. And the amount that goes through each of these branches is going to depend on the resistance of those branches, which in our fluid analogy is how wide or how narrow each of these pipes is. So here, this guy has the least resistance, and that means exactly what it sounds like. It's where the resistance is the smallest. So this is going to get the most current. This one has the most resistance. It's going to get the least current. I don't want to get too far off track here, but these are nice things to keep in mind as you're looking at these circuits, just to try to figure out. Sometimes you'll see some kind of really complicated circuit and it's not as obvious whether it's in series or in parallel. The defining characteristic of whether it's in series or parallel, they all have the same potential difference across them. And series, they all have the same current going through them. Okay, so back to the task at hand. I want to answer the question, what is I? The current I is just what's coming out of the battery. It's not the current that's going through each of three of these. It's the current that's the total current that's being drawn off the battery, and then will be split into three parts. So I go to my formula for resistors in parallel, and I say, okay, the equivalent resistance is just going to be 1 over R1 plus 1 over R2 plus 1 over R3. 1 over 100 plus 1 over 50 plus 1 over 60, you can check me on this, is something like 0.046. There's more digits after the decimal point here, but they don't have any physical meaning because I'm starting with something that, you know, in the statement of the problem, the most significant figures that I have, or the least amount of significant figures, I'm sorry, I have to be careful of what I'm saying here. The least significant figures that I have is 2 from the 10 and the 50 and the 60. This has 2 significant figures. So I don't want to keep more significant figures than I need. So in the end, I have 1 over R equivalent is 0.046. I have taken ohms and taken the reciprocal of it, you know, basically 1 over ohms. So I'm going to get inverse ohms as my units here temporarily. This is not the answer that I want. I need one more step. I want the actual value of the equivalent resistor. So I have to invert this equation to get this R equivalent back in the numerator. And when I do that, 1 over 0.46 is going to give me 21.4 with many more digits afterwards. And 1 divided by inverse ohms gives me ohms, okay? One last step, and I'm not banging you guys on this because you're not engineers and it's usually not important unless you're doing very precise work. And then it's, you know, life and death type importance. But in this case, I rounded this off to 3 sig figs. All I had in the beginning was 2 sig figs. So I want to take this back down to 2 significant figures, 21. Okay, so that's our answer. That's our equivalent. Okay, thanks. That's our equivalent circuit. And we get a equivalent resistance for this. Replacing these 3 resistors in parallel are going to be replaced with a single resistor, our equivalent resistor, which is 21 ohms. Okay, my battery hasn't changed. It's still providing 10 volts. My current hasn't changed. It's still the current that's being drawn off this battery, and that's what I'm trying to find. Remember, that's the start of this problem. What is the current that's being pulled off this battery? So my equivalent circuit is this simple circuit, 10 volts, current being pulled off, 21 ohms. And if I want to find out what that current is, I just go back to my friend, Mr. What was it? Mr. Ohm, and he tells me Ohm's law is the current that is the response to a potential difference is inversely proportional to the resistance, or in other words, I equals V over R. My delta V is 10 volts, and my resistance, this new equivalent resistance, is 21 ohms. So I get 10 divided by 21 is 0.48, and a volt divided by ohm, again, is going to give me amps, my SI unit of current. Okay, so we're almost at the halfway mark. I hope this kind of makes sense. Now's the time, if you want to please go ahead and ask me a question in the chat, or I will just kind of bang away ahead to our next topic. Okay, good. Seems like it's all clear. When we are doing these problems, if I rush through these problems, I will get them wrong. I have to take my time. I have to take, you know, each of these steps very, very slowly so that I don't make a mistake. And one of the things that I do is do a sanity check when I get the answer in the end. If you notice, in each of these situations, you have something interesting that happens with the result. So if I go back slowly to this bunch of resistors in series, I have 15 ohms, I have 30 ohms, I have 23 ohms. And the equivalent resistance, the total resistance, was 68 ohms, which is bigger than each of these. That's almost, you know, it's almost trivial. It's almost, you know, so obvious. You're like, why are you bothering me with this? Well, just keep in your mind that this number is always bigger than any of these individual numbers when you're in series. The opposite is true when you're doing parallel circuits. So here we had 100 ohms, we had 50 ohms, we had 60 ohms. If you play with this formula for the, you know, for the parallel circuits, you can convince yourself that you're always going to get a number that is less than any of the resistances that you started with. And let me show you again what we got here. We started out with 100, 50, and 60. The equivalent resistance turned out to be 21 ohms, which is smaller than this, it's smaller than this, it's smaller than this. If you look at this formula and you play with this with a couple of different numbers, you'll find that this is always true. So one little sanity check that I do for myself, and which, you know, I'm just recommending maybe you consider doing for yourself, when you're done these problems, when you think that you have the answer and you want to just do a quick sanity check to see, hey, did I get this right or did I get it wrong? One thing that has to happen is if you've taken a bunch of resistors in series, then the equivalent resistance has to be bigger than any of the individual resistance values. And if you have a bunch of resistors in parallel, the result that you get has to be less than any of the individual resistors. Okay, so it's not gonna guarantee that you get the right numerical result, but it's a sanity check to say, hey, did I do something that, you know, is a calculator mistake that I can catch myself so I don't lose, you know, I don't actually get the problem wrong. It's a way of checking that, you know, that you didn't do something completely wrong if you check these things. Okay, so I hope that helps. What I'm going to do is the next thing we're going to get into is capacitance, but I get bored of hearing myself talk, and I'm sure you do too. So why don't we take a moment here and take a look at a clicker problem. So what we're going to do is take a look at an example. I'll put the problem up here. It takes me a moment or two to get this polling up and running. We have a situation here where we have a bioimpedance analyzer. And this is something that would be used to measure body fat percentage by passing a current through your body. And your body is, you know, it's a conductor. It's a poor conductor, but it will conduct electricity. It will conduct current. And we saw a couple of lectures ago that muscle and fat have different resistivities. They will have a different value for the resistance depending on whether, you know, your body composition. So you can analyze the result here to dig that out. We're not going to actually go that far in this problem, but the question to you guys is, if I have a 15 volt potential difference applied across this resistor and I find that it's pulling 17 microamps off of the battery, what's the resistance of this poor guy that we're hooking up to this bioimpedance analyzer? I remind you that micro, this symbol here, is 10 to the minus 6. This small k is a 10 to the third kilo. This big M is a 10 to the 6th, and this little m is a 10 to the minus 3. So take a look at that problem, start working on it, and I will set up the poll. Hopefully you can see it, and I'll put that off to the side and go ahead and have at it. Feel free, just like in the old days, you can ask questions, you can talk to your friends, you can talk to me, you can send a private chat if you're embarrassed to ask a question in front of the group. Anything at all, just, you know, if anything's unclear about units or something like that, just feel free. Okay, how are we doing here? Basic idea for the people maybe who don't know where to go with this. We have a resistor, we have a potential difference across it and a current through it. I am not asking for equivalent resistances. This is just basically kind of a slightly more tricky circuit than what we've seen before, but nothing that you haven't seen already. Or nothing that you can't handle, I should say. Okay, so I'll give this another 30 seconds or so for those that are still thinking about it. Okay, and it looks like we got most people. That's about 2 minutes. So I'm going to end the poll. Let's see how we did. Okay, there's the results. And the answer is 0.88 megohms. So, you know, just walking the 40% of people here. So we got 60% getting it right. I got 40% of you that didn't get it right. But I guess what happened here, I don't want to speak for you, but my guess is, since the majority of people that got it wrong chose B or D, the actual answer is 0.88 megohms. So can I guess that you guys are just having a hard time converting what you got from your calculator into megohms, because you got the right numerical factor, but then got the wrong SI prefix. So 0.88 10 to the 6 ohms is the result that you've got here. Okay, so feel free to ask me a question. How do the units work in this? So the units here, we have a question from Francis. So a question from Francis: how do the units work in this? This is basically, you know, we're given units of microamps. So if you wanted to do this in SI, you want to do this as 17 times 10 to the minus 6 amps, and that puts me in SI as long as I, you know, take into account that 10 to the minus 6. The volts is SI volts, and then I'm just using Ohm's law here. So if I use volts in the numerator and I use amps in the denominator, I'm going to get ohms in the result, and then I'm asking you to then, you know, take out a factor of 10 to the 6 and call that a megohm. So Francis, I hope that answers what your question is. Basically, you know, we're using Ohm's law here, and the units are going to come out right if we use amps and volts to start with. The one tricky part of this, which maybe threw off 40% of you, was once I got the SI, which would have been, I think the number is some crazy thing like, let's see, so it's 15 divided by 17 exponent to the negative 6. So I get the number I get is 882,352, right? It's this big awful number. That's ohms, but that's, you know, 882,000 is 0.8 million, and a megohm is a million. Okay, so Francis, I hope that answers your question here. Okay, I can kind of see that now. Okay. That leaves me a little bit dissatisfied that you kind of can see it. If I can help clarify that a little bit more, please don't hesitate to ask. But yep, it's a 10 to the 6 type factor here that's, I think, throwing off 40% of you. All right. If we have time, we'll come back. We'll do some more polling after we introduce this topic here. I want to loop back again to our concept of capacitors. Parallel plate capacitor, I remind you, we have a conductive plate here and a conductive plate here. We have some separation of charge, which nature doesn't like. They want to be together because of that Coulomb attraction. And the separation of those plates is given by D. The cross-sectional area, I'm showing you the face-on, the flat-on view of this. You're to remember that these are plates. They have some, they have some cross-sectional area. So our formula for the potential across this is going to be the charge on the plate, each of the plates, divided by the cross-sectional area and the distance between them. Our epsilon naught factor is something that comes along and gets the units right for us. So I could solve this for the charge, the amount of charge as a response to a potential difference applied across these plates in this sense. Q, all I've done is just peel out this Q and put everything else on the other side of the formula, or the other side of the equation. So I get Q equals epsilon naught A over D delta V. And what I'm going to do here is just try to simplify this. This looks a little bit nasty. And what we're going to do is the Q comes along for the ride, the delta V comes along for the ride. Everything here that has to do with the geometry of the plate, I'm going to bundle up in this thing called C. I'm sorry, we're using we're using the letter C here again. We already used that for coulombs. We're going to use that now to find something called capacitance, right? So all I'm doing is taking this formula that you guys know and love and have used in homeworks and have seen for a while, and taking all this jumble and calling it C, just to make clear that there's a linear relationship between the potential applied across the plate and the charge that's going to accumulate on that plate. So this is the voltage across the capacitor. This is the charge on the capacitor. And when I say charge on the capacitor, I don't want to confuse you. That could mean the value that's on the positive plate, the positive amount of charge, or it could mean the absolute value of the charge that's on the negative plate. They are equal and opposite. But this number is always going to be that's the charge that's on this plate. Okay, so what we find here is this capacitance for a given, this kind of bundles up all the geometry and the characteristics of the particular parallel plate, and then it tells us if I apply a potential difference, this is the charge that's going to result as a result of that applied potential difference. That C is just epsilon naught A over D. Okay, so how can I, first of all, I just want to make clear that this jumble is characteristic of the particular capacitor. This formula is a general formula that we can apply to any capacitor, but the details of the specific capacitor are all bundled up in this number here. Okay, so we units are our friend. If we kind of keep an eye on them, it helps us avoid mistakes. So I'll take a moment here and talk about units. The units of capacitance are going to be charge over delta V, just from this formula, right? If I put the C by itself, I get Q over delta V. The units of Q over delta V are coulombs per volt. And a coulomb per volt in SI, we are introducing a new unit today. It's a great day. We introduce a new unit. It's called a farad. And a farad is named after a great physicist named Michael Faraday, who, one moment. So he was born in 1791, died in 1867. So he was alive during this time when people were, first trying to play with batteries and with currents and with electricity. And he contributed a huge amount of experiments and just empirical knowledge about electricity. And for this for this work, he's rewarded now. Doesn't make any difference to him now, but we have an SI unit named after him called 1 farad. I don't know if people have heard about Faraday, but he is one of the kind of giants of the early years of physics. Einstein, who was asked who were his most influential, or who he thought were the most influential or most important physicists, one of them that he named was Faraday. I think the other ones were Newton and Maxwell. But it's a guy that kind of slips under the radar. He's a big deal, and for that he is rewarded with this unit, a farad, which is 1 coulomb per volt. Okay, now what's the point of all this? We're not trying to honor Faraday. We're trying to actually understand circuits. What's the point of this capacitance thing? Well, the point of a capacitor in a circuit is to store charge. So you can imagine that, think about when I separate charge, I've created a potential energy difference, right? Because charge wants to be together. It wants to balance out. That's the Coulomb force that's always pulling it together. Or I can think of it as potential energy that once I have pulled charges, a positive and negative charge apart, they want to get back together. And that creates a potential energy, an increase in potential energy. So you can store energy. You can store charge by store energy by separating charge. And you could imagine that you might want a larger amount of charge for the amount of potential difference that you've applied to this circuit. So this C, the larger you can make it, this capacitance, the larger you can make it, the more charge you're going to have stored on your parallel plate capacitors for a given application of potential difference delta V. And you can imagine that this, why are we always talking about these parallel plate capacitors? Because they are a good model of a lot of things in nature. We talked about, the cell membrane, because you have this separation of charge on the inside and outside of the cell membrane, that can be modeled as a parallel plate capacitor. If you go into the health field and you have, these defibrillator paddles, you can think of these as, as a crude model. This is a parallel plate capacitor where we've stored a tremendous amount of charge on these plates. And, oh, by the way, you shock it through someone so that you can kind of restart their heart. But you could imagine that you want to get a large amount of charge on these plates. So the larger the C, the more Q you get for a potential difference. So with this in mind, we have a limited way of increasing that amount of charge because, okay, if I make C bigger, the Q is going to be bigger. But the only way that I can make C bigger is by increasing A or decreasing D. Epsilon naught is a constant of nature, and I'm stuck with it. As far as I know, it's been the same number for the past 14.5 billion years. It doesn't change, and it's not going to change in the foreseeable future. But you could change the geometry of your plates. You could change the area, or you could change the spacing and get them closer. But there's a practical limit to what you can do here. After a while, you get so close that the plates are going to be in contact, and now you don't have a parallel plate capacitor anymore. You just have a short. And the area, if I increase the size of the area of these plates, well, after a while, it becomes so big that it's not useful to put in circuits because we kind of like tiny things. We like small radios and small circuits. And you can imagine if your cross-sectional area of this capacitor gets to be, bigger and bigger and bigger, it's useless. You just don't want to carry around a huge capacitor like that. So the way people get around this, I'm not going to derive it again. The derivation is, one paragraph in your book. I'll let you read it if you would like. But it can be shown that you can boost this number by introducing in between these parallel plate capacitors an insulator. Remember, an insulator is just something that doesn't conduct electricity very well. It's something with a poor or with a large resistance. So I don't know, plastic, Teflon, water, something like that doesn't allow the passage of current very well. If I put this insulator in here, the characteristic of this material will be something called the dielectric constant K. And I'm not going to derive this, but the basic idea is I can boost this capacitance by introducing this material, this insulator between the parallel plate capacitors. It's a little bit counterintuitive, but it's a pretty straightforward derivation. In the end, what happens is this boosts the capacitance, this value of the capacitance, by a numerical factor k, which is going to be a number that is characteristic of whatever material you've stuffed in between these two parallel plates. Okay, so this k is a dielectric constant. It's a number. It has no units. It just multiplies this capacitance that we get for a capacitor which has nothing in between the plates, just vacuum. And just to give this some kind of context, I'll slow down in a minute and allow, basically ask you guys for questions. But the idea here is, if I have a parallel plate and there's nothing in between it, my dielectric constant is the constant of vacuum, and that has the factor of 1 exactly. So this formula simplifies to what we had all along, which is just epsilon naught A over D. If I have air in between those plates, it's essentially vacuum. There's really not much difference between air and vacuum. If you want precision at the 4th decimal place, you have to use this number, but never in this class would you need that precision for any of the problems that I ask you. So for air, basically the dielectric constant is 1 as well. Where things get interesting is if you start putting good insulators in between those parallel plates, and then we can amplify that capacitance. So for example, Teflon as my dielectric, it's a weird word, but it just means insulator. If I put some Teflon in between those plates, I'm going to be able to boost the value of that capacitance by a factor of 2 without changing the dimensions, not the cross-sectional area, not the distance between them. I've just put this, Teflon in between the plates, and that increases it. Cell membrane, if I compare what I'm going to get for the charge buildup across the cell membrane, here's my equation. The charge buildup inside and outside the cell membrane, depending on the potential difference inside and out that cell membrane, the cell membrane itself has this dielectric constant K, which is about a value of 9, right? So it's just different than what would have been if there was vacuum in between those two parallel plates. And then water has a really high dielectric constant. I don't think it's the highest dielectric constant. I think you can even get, some exotic materials with dielectric constant in the thousands or hundreds of thousands. But water is about the most, common dielectric that we could think of putting in between two conductive plates. Okay, so again, the idea of the dielectric is just to try to boost that value of capacitance, and the idea of the capacitance is that we want to increase the amount of charge that's on that plate for a given potential difference. So let me kind of let me show you our example here. We have I hope you can see my little demo here. We have a source of potential difference here. We have a parallel plate capacitor right here. The potential is being provided by this battery. The capacitance, the value of the capacitance is going to be shown as this vertical bar here. There's two ways that I can increase that value. One is I can decrease the spacing, and I very quickly go off scale, so let me kind of reduce this here. So I can decrease D, and that increases the amount of capacitance. If I increase the spacing, the capacitance gets smaller. If I decrease, the capacitance gets larger. The other knob that I have geometrically is I can increase the area, or I can decrease the area. And the last thing that I can do is I can take a dielectric and I can stuff it in between the plates. And this particular dielectric has a constant of 5. I don't know what it is. It's something between Teflon and cell membrane. I'm not sure what the actual material is, but I can multiply that capacitance by just putting this material in between the plates. Okay, so I hope that this little kind of cartoon helps clarify what I'm talking about here. And we're getting close to the end of the lecture. Again, the basic idea is we're using this capacitance to boost the amount of Q for a given potential difference across that parallel plate. The last thing I want to introduce without derivation, just kind of give it to you here, is we have this parallel plate. It's in a situation where I've taken the natural harmony of nature, where plus and minus live happily together, and I pulled them apart by some means. I have a separation of charge. It's an unnatural state. They want to get back together again. You could think of that as there's a Coulomb force of them coming back together again, or I've increased the potential energy of this system by separating them because they want to get back together again. How much energy is stored in this parallel plate by the fact that I have a separation of charge? It's kind of a gnarly derivation, so I'm not even going to do it. You can look at it in the book if you like. But the basic idea is how much work does it take to separate that charge? And in the end, you come up with a simple result that the potential energy in that system is going to be equal to 1/2 Q squared over C, where Q is the amount of charge on one of those plates, and the C is the capacitance that we've been talking about for the last half hour in farads. So we have Q squared over C. And if I look at my other defining characteristic equation of these capacitor plates, Q equals C delta V, then I can redefine this, just put this C delta V in that Q squared, and I can get a second equation, 1/2 C delta V squared. So that tells me the amount of energy that's on these parallel plates. You know, these parallel plates can be used for a lot of different things. One of them is just storing energy, and the energy storage is in the process of having these separation of charges. This is going to give me an answer. It's kind of a complicated equation in that I have squares and then all kinds of weird units, Coulomb squared per farads, that kind of thing. In the end, I know that energy is in joules, so this answer is going to come out in joules as long as I put my input in SI units. Okay, so that's kind of what I wanted to cover today. I hope it wasn't too much. I hope we're kind of going at a good pace. I don't see many people throwing up the go slow sign. I have there's one student that wants to make an announcement about some extra credit that she's done, so we're going to take 1 minute for that. And I want to also remind you that we have an exam coming up on Monday. I'll post more information about that very, very shortly. So Peyton, do you want to take a moment here and mention what you've done some research on?
Yeah, totally. So I've just been really interested in this electricity topic. So I did a little bit of research on this thing called War of the Currents, and it's a war between alternating current and direct current. It's Edison and Tesla, and I just hope you guys enjoy it. It should be on Canvas at some point today, but I just did a little bit of research because I just found it really interesting, and I hope you guys do as well.
Okay, thank you, Peyton. And I guess when you send that to me, I will post it on Canvas. I guess I'll put that under modules. So guys, take a look at that. As I understand it, this is a kind of a look at of the contributions of Tesla to our modern understanding of electricity. Is that right, Peyton?
Yeah, basically. It's just a little kind of project. Just to show, because how often do you really hear of Tesla in classes? You mainly hear about Edison, and I just wanted to inform and educate people that Tesla was a huge part of this electricity process and how the world came to be as it is today in the electric world.
Okay, thanks, Peyton. Thank you, everybody, for your attention and your patience, and I will see you all on Wednesday. Try to enjoy this beautiful weather that we are getting.